What's up, people? How's it going? This is Sundar, and welcome to my channel. So today, we'll be giving a virtual contest of the round 716 Division 2. So the thing about this round is, when I was a newbie, I attended this round and I pretty much messed up the whole round, and I was able to solve zero problems. That is, I wasn't even able to make up for one problem, and it has already been 1 year since back then. So let's try giving this contest a try, and let's see how it goes. So we have 40 more seconds. Okay, the contest is gonna start. Mm, Let's try it up now. Given an array A of length n, tell us whether it has a non-empty subsequence such that the product of its element is not a perfect square. A sequence B is a subsequence of an array A if B can be a okay, yeah. Saying that the product of its element is not a perfect square. Okay, so product should not be a perfect square. Mm, Okay, the thing is, if an element is not a perfect square, then we can just return that element alone, right? So should the subset size be greater than 1? No, it's not given anything of that kind. So the thing is, if some element is not a perfect square, then that element alone can be returned as an answer. And if all the elements are perfect squares, then if you multiply two perfect square numbers, it will just turn out to be a perfect square again, right? Yeah, that's pretty much it, right? That's pretty much it. So what do we need to do? We have to go through all the elements and we have to check whether every number is a perfect square. And the thing is, so for this 36, we'll be getting 6 into 6. So let's try taking the let's try using the square root function. And as the elements are not so big, it's just that it ends up 4. I think this one will work. So square root of 3 of 5. If x into x equals to the given number, sorry, if not equals to a given number, then we can pretty much print that number. And okay, we just need to print s or wrong, not. If it comes out of the loop, then there is no number which is not a perfect square, so we'll be printing not. I don't know why the website is so slow as of now. Did I make a submission or not? Okay, I have already made a submission over here. And okay, let's accept it. Okay, I was able to solve this question, which I wasn't able to solve back then. I don't know why I messed up over here. This is a simple question. Uh, and zero some big. Baby Badaw's first words were and zero some big. So he decided to solve the following problem. Given two numbers n and k, count the number of arrays of length n such that all its elements are integers between 0 and 2 to the power k minus 1. All its elements are integers, okay, between this range, between 0 and 2 to the power k minus 1. Bitwise AND of all its elements is 0. Bitwise AND is 0. Sum of its elements is as large as possible. Okay. So number of test cases you need to solve. Okay, that's pretty much it. And n and k is given, and here construct an array of n length n. The numbers are okay. The numbers can be the range to the power k minus 1. Sum of its elements is as large as possible. Okay, what does that mean? For example, 2 2. Okay, and should be 0. The elements can go from, okay, it's 2, right? So 2 to the power 2 minus 1. So it can go from 2 to 3. Sum of its elements is as large as possible. Okay, so sum of the elements in the sense, what's the maximum possible sum for a number or for an array with all its elements as 2 to the power k minus 1. Okay, all the elements are 2 to the power k minus 1. It will be 3 plus 3 is 6. Okay, the thing is, it will not be having an AND value of 0. Okay, maximum sum is 3. If we had to get an AND value of 0, then we're getting a sum of 2 to the power k minus 1. Is it? Okay. Uh, okay, what can I do for this? Okay, the thing is, AND value should be 0, right? Let's construct it like this. So we'll be having two numbers, so n numbers, and then it has, everything has k bits. Okay, so if it is 2 to the power k minus 1, if it is just say k is 3, then we'll be getting all the numbers from 0 to 7. And if you see from 0 to 7, so every number will be having at most 3 bits, right? So 3 bits. So if it is k, then a number in this range will have k bits. So this is one basic observation. And what can we do for that? Okay, there are n numbers. So there will be n numbers with k bits. Okay, so let's say something like this. N numbers. And then each one will have k bits. So these will be the numbers, k bits. So I don't know, some k bits. So just take us 3 or something. Another thing is, we need to have the AND value of all the elements as 0. Okay, so 0 means when okay, if you AND every bit, then every bit should have a value of 0. Okay, so these values should be 0. If it has to be 0, then at least one of these bits should be 0, right? Okay, that's correct, I guess. Because if you have something like this, then we'll be getting a 0. And there is no other combination with all the things as 1, which could give us an AND value of 0. Okay. So the thing is, at least one of these bits should be 0. So if it has n bits, then n bits, then we can, okay, I think there's a problem of combinators, I guess, because there can be many other possibilities, right? Okay, what are they asking? Since the okay, count the number of arrays of length n such that, okay, so we just need to count the number of arrays. Okay, I think we can do it in this way. So how many ways are there to fill all the, to fill at least one of these positions with a 0. So as there are n bits or n numbers, you'll be getting nc1, which is nothing but n. So there are n ways to fill up this value, that is this particular bit, with a 0. So even for this one, okay, there'll be n bit for this, sorry, n possible ways, and even for this bit, there'll be n possibilities. In for the thing is, we are just considering one case, but there can be 0 in this one, 0 in this one, and still the n value will be 0, right? Okay. So what are they even doing, man? 2 2. If we have 2 2, 2 2 in sense 2 n 2s, n is 2, and then k is 2. So let's say I try to put 0 in both of these. So I'll be getting a n value of 0 and 0 and then 1. So yeah, okay, this one works. Okay, this is a 0 and 1 combination. Okay, okay. So they don't even have a 0 and 1 combination over here. Why is it so? Uh, Even this gives us a n value of 0, 0 1. Okay, if you don't have all its elements or integers both between 0 and k to the power k minus 1, yes, it follows. And value is 0. Okay, sum of its elements is as large as possible. Okay. So it doesn't follow the condition, I guess. Yeah, 0 plus 1 is 1. But the thing is, we can get some value of 3. So, okay, yeah, I think the thing is, if you just put one value or assign one of these n values 0, then we'll be able to get a value of 0 over this bit, right? So the thing is, if you just put another 0 in the same position, then it will reduce the sum of ours. So we'll not be doing this. We'll not be doing, or we'll not be putting two zeros at the same bit, and we just need to assign any one bit among these n numbers as 0. Okay, yeah, I think I got the answer, because so we just need to set one bit and then put 0. Now if you put 1 over here, we'll be getting 0 3, and this is a good combination. And if we put 1 over here and then 0 in this case, then we'll be getting it's 2 and then 1. Okay, yeah, we are getting the answer at this. Yeah, we are getting the answer. So one bit among these n numbers should be given a value of 0, and for that we'll be getting nc1 possibilities, and for each bit, for each k bit, there'll be n possibilities, right? So n into n into n into, okay, n k times, it will be n to the power k. I guess n to the power k should be the answer. Yeah, okay, that's straight up, man. Uh, okay, what are the submission counts? Okay, it's already 1500, so I guess this one will work. Because I think this is a trivial question. Many people will be able to do this. Okay, so we have to take the modulo by 10 to the power k minus 10 to the power 9 plus 7. Okay, I think we had to use binary exponentiation in this. Okay, so a comma n comma mod. So a modulo equals to mod, and then till this n becomes 0. So we'll be doing n by 2 at last, and each step, if the n is odd, we'll be adding up or multiplying that answer, multiplying a to the answer. So we'll be adding some variables. So result is equals to result into a, and we have to take the modulo along with that. Okay, modulo is 10 to the power 9 plus 7. I did not give this one. Just give this parameter. Okay, it's small, and it's also that I had to multiply a with a. Okay, I guess this is like this is so we had to calculate the power. I'll be storing it in x. So bin pow of n comma n, and the value will be just x. I think this should work. Let's see. 0 0 what? Um, why is the answer kind of 0? Okay, we had to return that. Okay, I haven't even returned the value of rest. Okay, this works. Let's say submit this code. Accept it again. What about the standings? Okay, so 116 people had done this problem. 2000. I think C was a pretty simple problem. I wasted a lot of time. Maybe. Okay. Now you get baby Ahab's first words. Given an integer n, find the longest subsequence of 1 till n minus 1, whose product is 1 modulo n. Whose product is 1 modulo n. Please solve the problem. A subsequence, okay. Given an integer n, find the longest subsequence of 1 till n minus 1, whose product is 1 modulo n. So here are 5 numbers. Product is 24, which is congruent to 4 modulo 5. 4 modulo 5, whose product is 1 modulo n. The product here is what? 24 which is congruent to 4 modulo 5. Wait. Product of the product of the elements is 6, which is congruent to 1 modulo 5. Okay. The only longer subsequence is 1, 2, 3, 4. Its product is 25, which is 4 congruent 5. Hence the answer is 1, 2, 3, 4. Okay, so we have to take as many numbers as possible such that the product modulo of 5 or product modulo n should be equals to n model 1 modulo n. So that is the product modulo n equals 1 modulo n. Okay. Is it some dynamic programming or okay, we can't produce all subsets. Okay, it's recording. I just checked that whether it's being recorded or not. 1, 2, 3. Because our product of elements modulo n should be equals to 1 modulo n. 1. Okay, the thing is, it should be the modulo should be 1, right? Modulo should be 1, and we had select numbers such that modulo is 1. Modulo is 1. Okay. Product modulo n. What can we do with this? Okay, for 4, for 8, they are selecting 1, 3, 5, 7. Product modulo 8. So if you take any number from 1 till n minus 1 and take the modulo by n, so it will just be the same number because all the numbers are less than that. And numbers. Should get a model of okay. So let's say we have numbers from 0 to 7. Okay, 1, 2, 3, 4, 5, 6, 7. Model by 8, 8, model by 8. Okay, I think a small if it was modeled by 8 and then we had to get a remainder of 1, so the answer should be like, I mean, the product should turn out to be something like it cannot be 1 because, yeah, it can be 1. But the thing is, we have to get the longest subsequence. So the minimum answer will always be 1, of course. So it is 8, it will be 9, or the thing is 16 plus 1, 17, and 8 3s are 24, 24, 25. It can be a value of 25, or 32, 33. So 5 times is 40, so it can be 41. 41. Okay. So these are pretty much the possibilities. Okay. The thing is, what can you do with these numbers? Okay. Okay. We have to pick some number out of the possible values and we can try to construct that number. But will that even work? No. So in this case, we have for 8, the modulo of 9 will give us value of 1. The thing is, we can't construct 9 at all because 9 is 3 square, or if we just have 1 and 9, we can construct it, and it will not be optimal because it will just be having a length of 2. So in the case of 17, 17 is just one number because it's a prime number. In 25, it's also two numbers. 2 numbers. I can't construct that at all. 33, 33 means 3 and 11. Uh, okay, what can I do for this? So, okay, the whole product should be of the form nx in nx plus 1. Nx plus 1. Okay, nx plus 1. So the thing is, whatever product that we get should be of form nx plus 1. And nx plus 1. Okay, how many have solved this? 300. Okay, I think there's a pretty good problem or something because submission count or the accepted count is just 320 as of now. Now let's think. Uh, nx plus 1. Nx plus 1. So we have to take some numbers randomly. Okay, 1 can always be included because it does not matter. Um, What if we somehow include a number that is always one higher than this? Like, okay, what are they doing for 8? 1357, not 1357 in the sense 3, 15, 15, 7, 35, 105. Okay, 13 into 8 plus 1. 13 into 8 plus 1 this. Uh, and n goes to 10 to the power 5. So 1357. And if you see none of the combinations are divisible by 8, okay. Okay, okay. I think we can do it like okay. This will not work. Okay. At first, can we somehow get the value of the product? The thing is, if we get the value of the product or the product, if we redefine some value for the product, then we can derive the prime factors of that product, and then we can create or build up the value from these numbers, I guess. Oh boy. Okay. Um, mm, product those values not there. Okay, so 10 to the power 5, 10 to the power 5, 10 to the power 5. Okay, it forms a pattern of n plus 1 to n plus 1 to n plus 1 to n plus 1 and so on. So what can I do with this? If I give this number, then I can try making this up. Like I can try making these combinations. So I can traverse in the last or some number and try to construct that number using these numbers, but how to construct this number in the first place? Okay, so okay, well, a solution of 10 to the power 10 to the power 5, right? 10 to the power 5 now, n for producing all the products. The thing is, for every number, I had to take the prime factors or the divisors. I can do that in the square root of n, so it can have a complexity of nearly 10 to the power 7.5 or 7 10 to the power 7 or something. But will it not time out? Yes, it will time out. So if I try to produce all the sequences, or not sequence, all the n plus 1 to n plus 1 numbers and so on, and then try to take the prime factors of that, and then check and check the count of the prime factors. Like if it's 2 to the power 4, then I can construct that using 2, 4, and then 2, 4 is what? 2 to the power 4 is 8. It already 8. So then I say I had to 2 or 2 or 4. So I can construct it using 2 and then 2 to the power 3. There's two numbers. So if I have the prime factors, of some number. Let's say if it was 2 to the power 4, they can use two numbers to construct it. That's why I can optimize that. I mean, maximize that. If I have 2 to the power 5, then what it means is I can use 2, I can use 2 to the power 2, 3 to the power 3, and 2 to the power 3 already. So 2 to the power 4, 4. Okay, the thing is, okay, I got it. So if you have 5 numbers, I mean 2 to the power 5, then we can use 2 numbers to construct that because we're having a binary value of 101, so we can do that. So if it's 2 to the power 6, then it will use 2 numbers, that is okay. I think I can use this method, but I don't know whether it will time out or not. Um, what's the solution count as of now? Okay, it's 600 something. Uh, should I try putting this or wait. Mm, yeah, okay. I think let's say we have uh, 8. Okay. So the thing is, if we just take some number like 2 in it, so let's say we have 2n or something, it can never produce a value or a model of 1, right? So, so whatever combination we make it along with this 2, let's say we take 2, 3, 5, some number randomly, it will always be even or um, will somehow be divisible, not divisible, but 2 into 3 into 5, what's that? 6, 6, 8, 13, that will be 8. Okay, okay. So the thing is, if n is there, then n n is there. Hmm. Okay. Okay. You're so hard. Mm. 3 into 5 into 7. 5 into 7. Mm. Okay, so all these numbers are not at all. I mean, 8 doesn't contain any of these numbers. 8 just contain 2. Okay, and these numbers 3, 5, 7 were not factors of 8 at all. Okay, does that even matter? think we need not produce all the subsets, or I mean, we need not produce all the possibilities like n plus 1 to n plus 1 and so on. The thing is, what I have observed is if I take any number, let's say it is n, so 8. So if I take any multiples of this 2, like 2, 4, and so on, so we can replace if this one is included in this product, then thing is it will be like 2 times of some product. And this can never be of the form n plus nx plus 1. So in the case of 4, it will be 4 into something, and then is 4 into something will be carrying some of the multiples of this 8. So it will be coming in this sense. Hmm. Okay. If I include this number, then what will happen? If I include this number to the answer, then actually, is this correct? Yeah, I think this is correct. Yeah. See, let's say we have something like this. So I think we should not include any factor of the same number, because if we have some a number like 8, okay, if let's say I include 4 in this. Now, if we try to produce all the multiples of 4, like let's say 4 into 5 is 20, and 20 modulo 8 will again be 4, because 8 it will be 16, 20 minus 16 will be 4, right? Now 4 into 6 is a multiple of 8 itself, so it will be 0. Otherwise, we'll be getting something like 4 into 7, it's 28. The model will again be this is 4. So 4 into 8, okay, it's 0. So 4 into 9, if you see, what's that? So it's 36. So the thing is, if it's 36, then we have a multiple of 32 for 8. So the model will again turn out to be 4. So if we include any of these multiples of 8, then the modulo turns out to be the same number, or it can also be 0. So in order to get a modulo of 1, you should not include any of the multiples of the same number, I guess. Okay. So, hmm, okay, okay. Okay, I think that's correct. So the thing is, we have to include all the multiples, I mean, all the values uh, that are not included in the prime factorization of 8. So if it is for 8, then we can only include numbers like 3, 5, and then 7. Otherwise, let's take 3. So 3, some multiple of 3 will be 12. So 12 modulo of 8 will not be 3. So it's not equal to 3, that's it. Yes. If we include some multiple, then the answer of the modulo turns out to be the same number. And if you take 5, so 5, 5, 6 are 30. So 30 modulo 8 will be 6, and it's not equals to 5. Okay. Okay, it turns out to be 6, and it's also logical, right? So 6 has two factors, like 2, 1, and 3. And then this 2 comes in the prime factorization of 2. So if you take any coinciding factors, then the answer turns out to be the same number. So I think that's the main observation here. So the thing is, what we can do with this? Okay, let's try these numbers then. So we have 3, 5, 7. Um, can we include all the numbers that are not coinciding with 8? No, it will not give a value of 1 for sure. Okay, not give us a value of 1. Okay, so okay, let's see, like, what if we multiply all these numbers as as the value for, I mean, as the answer for this is 3, 5, 7. Hence, if multiply everything, we'll be getting 1. Okay, let's take a different sequence or something. Like, let's say it for 7, 7. So for 7, we should take non-coincident factors. Like 2 we can take, 3 we can take, even 4 we can take, 5. Okay, as is a prime number, we can take everything. Now the thing is, we multiply all these numbers for again. 2 into 3 into 4 into 5 into 6. Okay, it's 6 factorial. Okay, it's 720. 720 by 7, or the model of it. So it's 1, 2 times 14. So we'll be remaining we'll be having a remainder of 6. Okay, so 6 we have having. Now how to, okay, we should get a value of 1. Now how to pick these numbers so that we get a value of 1? It's just correct 160 by 7. 2. Okay. So it's 1 or 2, 7. Yeah, it's 6. Okay, this is correct. So we'll be getting a model of 6. Okay, so model of 6 in the sense we have to eliminate. Okay, we have to eliminate all the numbers that causes small of 6, right? Only then we can gain something which is 6. So let's say I eliminate this 6. Now is it now is this value divisible by, I mean, is this value give us a modulo of 1? Okay, anyway it's 120 because 5 factorial it is. So dividing it by 7, we'll be getting 1 times, and then 5 will be the remainder for 17. It will be what? 449. So 1 will be okay. So we're getting a 1 remainder of 1 if we take all these numbers and eliminate the 6. Okay, so just by eliminating the modulo, we are getting a value of 1. Okay, so I think, is that it? Okay, let me verify it first. Okay, 120 happening. 120 by 7, 17, so 17 into 7. Okay, yeah, 119, yeah, we're getting it. So the thing is, if we include all the factors, okay, all the non-coincident factors, because if it's coinciding, then okay, the thing is, if it's coinciding, then we anyway have to eliminate those factors because it will never give us a value of 1 with that. Okay. So if I eliminate 6, then it's 1. Let's say I have 6. Okay. So I'll be getting all the numbers from 1 till 5. 4, 5. Okay. Mm, physical limit, it's to 23. Okay. So I don't know what to do over here. By taking this, I'm getting 1, but will it always be satisfied? Okay, let's try for some different input. If we have all the non-coinciding factors, so the non-coinciding factors are just 5, right? 5. And then it is also 1. And the modulo of, if we include all these numbers as a whole, then we'll be getting a modulo of 5. Then I had to eliminate 5 because it is the one which is causing the model of 5. So I'll be getting a model of 1. Okay, so we are having just 1 for 6. Is it correct? Okay, what do they have? 5. Okay, they have given an example of 5. Let's try of 5. So 5, if we take all the values, like we can take a number because it's a prime number. So if all these values, then the sum or the product is 24, and 24 modulo of 5 is again 4. Okay, I can also enter 1. Uh, now I'll be eliminating 4 because it is the one which causes the value of 4. Let's say we also have something like 8. We can't have 8, can have 8. If the thing is, if 8 is included in the sequence, now should I eliminate that 8 or not? Let's say the modulo is 4. Now if I just eliminate that modulo of 4, then okay, I think we don't need to eliminate, right? So the thing is, let's say we are getting some value till here as x. Now the thing is, I'm multiplying 4 and then I'm taking the modulo of it, right? So if this one is 4, then the previous value should have been 1. Otherwise, I would not be able to get a modulo of 4 again. So if I had to multiply 4 with some number and I'm getting the result as 4, then the previous number should have been 1. So if it is 4, then if I eliminate 4, then I'll be getting a modulo of 1. Okay, the modulo is what? Product is 6, 6 modulo is 5, it's 1. Okay, I think that's pretty much it, right? That's pretty much it. So we had to eliminate all the points-array numbers and then include everything. Now, if this value is something like, okay, it can be any value, right? It can be any value, and we have to take the modulo. If that modulo contains some number like 6, okay, if it is already 1, then we can include all the numbers. If it is 6 or something, then we have to go there and then eliminate all the possibilities that make 6. I think it's not all the possibilities because anyway, there will be only one 6, right? So what if we did not even include any 6 and the answer comes out, okay, there's no way that we don't include the 6 and then the answer turns out to be 6. So uh, can there be something of the kind? Okay, so always eliminating only one number. I think so, yeah. Let's see. Um, was 7, right? Okay, 7. Even 2 into 3 will be giving a product of 6. So should we also eliminate them? Okay, if we eliminate them, then will be 20 modulo 4. Okay, 20 modulo 7 is not at all 1. I think we just need to eliminate one number from the given sequence. Because if we just eliminate this, then it will be having a model of 1 because it would have already been 1 if we exclude this. And now if we try to include this 6, so this value will already be less than 7 because as we've already taken the modulo of it. And even this has a modulo of less than 7. Now, if we try to take the product and then take the modulo by 7, then it will give us a value of 6. So if I eliminate this 6, then I will always get a value of 1. I think this is correct, but I'm not able to prove it completely. Okay, let's try. Let's try, man. Let's try. Okay, what's the submission count? Okay, it's already 1500. The first step is what? First step is like including only okay, removing the coinciding numbers. Right. So avoid coinciding in the sense what we should not include any number that comes in the prime factorization of like this one. So it's 8, then if 8 we can't include 2, 4. What in the case of 6? 6 has 2, right? Okay, 6 has 2, and even that can't be included. Okay. For once, let's try including all the numbers in the sequence. Like, why not eliminate few numbers? Like, let's say for 6, I take all the numbers like 1 till everything, every number from 1 till 5. So I'll be getting 120, and of course it will be divisible, right? Okay, it will be divisible by this because we'll be having 2 and 3 in the middle. We'll be okay, for 8, it will be like, okay, even it will be having 2 and then 4 in the middle. So only if we implement all these factors, then we can uh, produce a model of 1. Okay, so eliminate 6. Yeah, that's it for this. Hmm, contest, contest. Okay, I think they should work. That's right. So we had to eliminate because let's say I include this 2. Okay, so as soon as I include this 2, the thing is it will always give us a model of 2. The thing is we'll be including 2, and then we'll be having this sequence, and this will be like, as it has already a factor, like this can be written as 2 into 3 or something. 2 into 3, 2 into 3. So model of 6 is nothing but we'll be eliminating all the multiples of 6 from this whole value. Okay. So mm, okay, so like let's say we have something like this, right? But the thing is, we have to prove somehow that we should not include these coincident factors. Otherwise, I don't know how it will work. Let's say we have some factor k. Okay, so should I prove it first or should I prove it because it's already 1600? Okay, but I don't know whether this one will work or not. So what's the proof that if I should never include any of these multiples? I think by just observation, if I take this 2 and then take some multiple like this 5, and it will be 20, and if I take the model of it, then it will be 18, and then I'll be getting a model of 2. Then is it always valid? I just observe this, but I don't know whether it's always valid. Let's say we have k, and then k is some factor of it, and even the number that is n also contains a factor of k something. So k into this also some factor. Let's say the whole number that's remaining after doing n by k is, let's say it as x. Okay. Now the thing is, we have to prove somehow that By observation, every number, there's every number on the left hand side, if it's been taken a modulo of n, then it leaves a remainder of k. That's what I observed. But let's try, like, let's say this is y or something, and so okay, we can write y as something like this, like x plus some other number. Now the thing is, okay, this one will be like xk plus kz. Now as kz is the n number, n value, so if we do a model of n, so this will be redundant. So only thing is, only thing that remains is this. So kz modulo n. Nothing else. Z can be anything. So let's say like 2, right? 2 into 5, 2 and 5. So 2 into 5, and the value of 6 is, means 6 can be divided as 2 into 3. Okay, the model. Okay, this can be written as 2 into 3 plus 2 into 2. Okay, so this one will go. So we're getting 4, which will be okay. So we're getting 4. 20 is, I mean, 6, 6, 18, 18. What is this one? What is this? 2 into 3 plus 2. Okay, okay, 3 plus 2. This is 6 plus 4. Okay, the value is 10, right? 10. 10. Okay, the value is will anyway be 4. It's not always k, it's some value of 4. Okay, I'm very much confused. 2 into 7 is 14. So 14 modulo 6 is 2. Okay. Okay, so is it always 2 and then 4, or can there be any other repetitions? Like, let's take 19, sorry, 9, so it will be 18. There's also all divisible by 6, so let's in this case. So 2 and then 11, 22, 22, 22 modulo 6, right? 22 modulo 6. The last value was 18, so it will be 4. Okay, so okay. So it is 2, otherwise the counterpart of it, like the subtract and the difference. So the thing is, if I don't include this 4, but okay, if you see 2 is there, and it leaves a remainder of 4, and even this 4 is coinciding with this 6. So we'll be getting a value like this, and k into z, k to z. There is the remainder, I mean not remainder, it's left out part of it. Okay, I think we can write this one as, okay. Okay, I pretty much called it, I guess. Okay, I think I have got the proof, some proof. Okay, so we have y. So we can write y as by Euler's, not by Euclid's division lemma. So we can write this one as a, b plus remainder, right? Now let's say we have x, sorry, k, and then y for some number, and then n is given us, sorry, n can be factorized as k of k. So okay, so let's say some coincident factor is a. A is the coincident factor, and this is k. This is a common factor. Okay, k is the common factor, and we have another number like a or something. Now, as this y can be written as, okay, as this y should be written in terms of this a. Okay, let's not denote this k. Let's have some other numbers there or something. Um, so it will be a is there plus r. This r is nothing but it's the remainder when we divide y by a. So if you see, this value will always be divisible by az, as it contains k and a, so it is equals to n. So it will use a remainder of 0. Now the left part will be k into r. Now if we try to divide or take the remainder of this value with respect to k, with respect to ka, so this is the value that we need, right? This, because this redundant. So we just need this value. And if you see, this r is always lesser than a, because r is nothing but it's the value that's left after we do y modulo a, y modulo a. So the thing is, I guess k into r is always value, because if it's k into a and r is lesser than a, then the value of k r, k, I don't know, I'm just pretty much messing up the whole question, I guess. Okay, k r should be less than k a, right? So if some value is already lesser than, and we take the modulo of it, then the value will always be k r. So if it contains some coincident factors, so there's some numbers like 6, and we take a value with some 2 or something, and we have another value here. So whatever number that comes over here will have 2 into the remainder of this, let's say k modulo 6. Okay, so the thing is, this number can never be 1. Okay, I think this is the proof of it. So as this number will always have this 2 factor, and will be 2 into some remainder of it, and as this remainder is always lesser than the prime factors of it, like if it is 2 into 3, we'll be getting some number here which is lesser than 3. So this value will always be less than this value. So the the modulo, if you take by 6, then it will be just 2 into this remainder part, and it will be lesser than 6 for sure. So the thing is, as it contains the initial value, the coinciding value already, so it can never be 1. Yeah, the value can never be 1, so we have to eliminate this term for sure. Okay, I think I got a proof of it. I think I can take now. So first we have to find the coinciding factors. I mean, we should not include any coincident number, because if we include the number, then the modulus will be in terms or in multiples of that number. Like if you take 10 and then 4, I mean 10 and then 6. So I construct 10 as 2 and 5. So not 10. The thing is, I should not include 2. That's what I'm trying to say. So as 2 is coinciding with one of the prime factors, now if I try to take any number, or the remainder that I will get will have a factor of 2 for sure. So in this case, it will be remainder will be 4. So 4 is nothing but it has has a factor of 2 because it is 2 into 2. So the thing is, if you include any coincident numbers, then those factors will always be there, and it can be in reduced form or something. So anyway, we had to exclude these coincident terms. I think we'll be including all the non-coinciding parts. Like if it's 6, then we'll be including 5 or something. Or if it's 8, then we'll be including 3, 5 or something. Now the thing is, whatever number it may be, so the answer that's coming at the last will be in terms of this. So it can include a value of 3. So if it includes a value of 3, then it means that we had to eliminate this particular value so that we get a remainder of 1. I think that's pretty much it. Okay, let's try to code this value, but how to code this? We had to eliminate the coinciding parts. So 8, we had to exclude 2, 4, 6 and 7. Okay, so 2 can be should I produce all the factors of 8? Okay, so it's okay, if that's the case, then I had to also produce all the factors of 6 and so on. Okay. So we had to just check the coinciding factors, right? We can just take the GCD of these numbers. If there's not one, then it has some coinciding factor. But I think I'm pretty much late. So okay, it already has a submission count of 2000. Okay, so everyone done till 3. Okay, that's right. I think this should work. But if it doesn't work, then I don't know what to do. If it doesn't work, then I think I will be brute forcing for all the values. Like I'll be producing n plus 1, n plus 2, n plus 1, 3, n plus 1, and check. Can there be any possible? But that's a very tedious task. I don't know. Okay, let's try this one. So we'll look at the value of this. Now I had to include all these numbers from 1 till 1 till n minus 1. So 1 till n minus 1, right? So 1 till n minus 1. Okay. N minus 1. Now if this value, okay, so the thing is, we just need to multiply these numbers. So let's say we take the multiplication of the product and x. So whenever the GCD, okay, we had defined GCD, GCD of a comma GCD of b will be nothing but if the value b is 0, then return a. Otherwise, return GCD of b comma a modulo b. Okay, if this GCD turns out to be GCD of 1 and GCD of I and then n turns out to be 1. If it's 1, okay. If this is 1, then it means that there are no coinciding factors, and I can include this number. Okay, I'll be multiplying x with this particular number. Okay. So now the thing is, I have to eliminate. Now let's say this is not x is not 1. Okay, if x is 1, then I can just we have to print those numbers, right? If I have to print, then I have to store somewhere. Okay, let's take some vector. Print vector. Okay. Now, if this value is valid, then I'll be pushing back the value. Pushing back these values into print vector or something. Okay. Now the thing is, if x is 1, then I can print all these values all together. Okay, so then I can just print the numbers in this print vector. Okay, and then return value. Okay, else the thing is, if x is not equals to 1, then we have to eliminate all the factors, not all the factors, but all the numbers that is equal to this x. Like when it was 1, when some modular turned out to be 6, so we were we so when the model was 6, we just eliminated the 6, right? So we just need to eliminate that particular x value. Let's say, okay. So after doing after taking the multiplication, we just need to take the modulo by n. Okay, will it somehow go out of the range? That is, will it overflow? To the under about 5, under about 5, under about 4. Okay, I think there's overflow. So we had to take the modulo of it over here. So after this one, let's say I take the modulo by n. Now things that will contain the modulo which we have to eliminate it from the given array. So I can take all the values that are not present in this array. So I guess the value of it okay. So this one will be um, okay. The number of count of all the values in this print array will be nothing but print the size, right? Print the size. Okay, so this is okay. And let's say we have some modulo like modulo x6. So the thing is we have to eliminate that 6, right? We just need to eliminate those 6. And the thing is there could be only one 6. Okay. So I had to print the number of count in the remaining array or the resulting array will be print of size minus 1 for sure. Because I just need to eliminate one factor, that is the x from the given array. So the thing is, I'll be going through all the values in the print array, in the print vector. So this value is equals to x, then I should not include this value at all in my array. Otherwise, I should print this value in the console. Yeah, I think that's pretty much it. Yes. Okay, so I'm getting AC so here. Okay, I think they should work. Let's try for 6. Oh, wow. Okay. For 6, it's 1 1. Yeah, we checked it over there, right? For 7, yeah, including all terms, till 5. We should give the value, okay. Let's say, we print the value of x over here. Okay, x turns out to be 6. So we'll be eliminating 6. I guess this should work. Okay, let's try. Okay, yeah, it got accepted. So the thing is, you just need to eliminate all those coinciding factors in the sense the ones which have the series 1, we had to eliminate them because as proved over here, so if we include them, then we'll be getting a value which is of form kr, and this k is nothing but it's the coinciding factor. So the factor will be, I mean, the number will always be including that factor, so it can never be equal to 1. So we cannot multiply any other number with it. And let's say we try to multiply some other number. So even if we multiply other numbers, the thing is it contains the same coinciding factor, right? So this can again be of the form k of y, and it will just go through the same process like over here. So the thing is, if you just include this factor, then it will always be containing this factor as my modulo. I mean, it will be included in my modulo in some form or the other. So yeah, I think this works. Okay, so it's already 46 minutes. Cut and stick. Let's get standings for once. Okay. Gallon, colon, neck. This was me in the first place. This was when I attended this contest as a newbie. I wasn't even able to solve one. Okay, but the thing was, now I was able to solve three problems. Okay, now let's try this cut and stick. Baby Ehab has a piece of cut and stick with an array A of length n written on it. He plans to grab a pair of scissors and do the following to it. Cut and stick with an array A of length n written on it. Okay. Pick a range L to R, cut out every element in the range. Stick some of the elements together in the same order they were in the array. End up with multiple pieces where every piece contains some of the elements and every element belongs to some piece. Now forming he partitions the sequence, okay, the some range into sequences. He thinks a partitioning is beautiful if for every piece it holds that if it has length x, okay, every piece sequence it holds that if it has length x, then no value occurs strictly more than x by 2 times in it. Then no value occurs, okay. He didn't pick range x, so he's wondering for q queries LR, what's the minimum number of pieces he needs to partition the elements into so that the partition is boy. I don't understand the question. Okay, the some array we have, and then we are picking a range and then cutting these values and then stick some of the elements together in the same order they were in the array. End up with multiple pieces where every piece contains some of the elements and okay. Now finally he partitions this range into some subsequences. He thinks the partition is beautiful if it contains for every piece. If for every piece, if it has length x, then no value occurs strictly more than x by 2 times. Okay, I think we have okay, so 1 to 6. Firstly, you can just put the whole array in one subsequence. Since its length is 6, no value occurs more than 3 times in it. Now for 1, 2 to 5, we have the range is this one. You can't put them all in one subsequence since its length is 4 and 3 occurs more than 2 times. Okay, however, you can partition it into 2 subsequences, 3 and then okay. I guess okay. What? Okay, can we do more than 2 partitions? How many partitions should I do? Is there some number of is there some upper bound for that or okay? Here didn't pick a range yet. So he's wondering for Q queries, what's the minimum number of pieces he needs to partition the elements, these things, into so the partitioning is beautiful. Okay. So we have been given a range and then we have to divide these numbers into some number of partitions such that the number of counts should not exceed this array, right? I mean this range. So the thing is, range is the range. I mean the number of distinct or the number of repetitions could be at max x by 2. Okay. I think I got the question. Now let's see. So we have so in the range 2, 3, 3, 3, right? 2, 3, 3, 3 we have. Okay, so greedy. No, greedy will not work, right? Okay. Both of n and q will be 10 to the power 5. Okay, so greedy will not work for sure. Mm, okay, let's see. Let's It's like there should always be Q queries. So Q queries is something but 3 to the 10 to the power 5. Now the thing is, will be given a range, right? So if we had to access that range, then we can't use the inspire solution. Inspire in the sense n into Q solution. So Q is a must to be included in the time complexity. So the thing is, we had to iterate somehow on the array, right? While iterating, as we already have Q as 10 to the power 5, this Q is already 10 to the power 5. So somehow we had to iterate on the array. So it was already 10 to the power 5, and the maximum of the operations that we can do is 10 to the power 7 or 10 to the power 8, okay, or 7. So the thing is, we can just do 10 to the power 2 iterations or 3 iterations. Okay. So this is the urban. Okay, I think yeah, that's pretty much okay. So these are the extra number of iterations that we can do on the given array. And it's also that given array can be of size 10 to the power 5, right? Okay. So 10 to the power 2 is nothing but its square root of it. Uh, so while iterating, we cannot exceed square root. Okay, we can't do any iteration in square root, but maybe okay. I think it will be like log and or something. Okay. So the iteration on the array should be something like log n, right? Otherwise, it will give TLE. Okay. Okay, we have 40 minutes. Okay. So the iteration on the array, maybe I guess it should be log n or something. Log n means we just have binary search for log n. Yeah. Okay. So we just need to do some kind of binary search on this. The thing is, I don't know what to do. Let's see. We have 2 till 5. 2 till 5. Okay. Now we have to partition this array. What's the array? Oh, okay, this range 2 till 3. 2 till 5. And we have 3, 2, 3, 3. Okay. So the number of count count of any number in the particular partition should not exceed 5, then not 5. 5 minus 2 is 3, 3 plus 1 is 4, 4 plus 4 divided by 2 is 2. So the number of, the count of repetitions should not exceed 2. Okay. Um, so how can you brute force? How can you do binary search for 2? It will always be linear, right? If there is a range, and we had to check, we had to partition this array or this range into some sequences which have a frequency of just 2 in this case, without even traversing the whole array. How can you decide that? And it's nowhere given like n into q cannot exceed 10 to the power 5 or not. So the thing is, both can be of the form 10 to the power 5 and 10 to the power 5. So if there was a statement like the total number of test cases or total number of traversals will not exceed 10 to the power 5. That is, n into q cannot exceed 10 to the power 5. Then we can do n into q or some kind of solution. But we can't even traverse the whole array. Okay, so okay, the numbers in the sequence goes from 1 till n. Is that useful in any case? Yeah. Mm, I will search on. Okay. Uh, 3233. So we have to find the number of partitions here. So they're partitioning at like elements of the query or this one. So they're partitioning with three as separate subarray and then 233 as a partition. I think that's not important. Right? We just need to find the number of partitions. Okay, number of partitions are needed. So we cannot traverse the whole array. That's pretty much sure, I guess. So we had to do some kind of login solution. But how can we even do a login solution for this? Uh, login solution. Okay, so login solution. Okay, what is only one query was given? Uh, okay, doesn't matter, I guess. Okay, okay. If you do hashing, anyway, that will be a linear solution. Okay, I thought we can put it in a map and then check whether any number has exceeded the frequency of x by 2. If it exceeds, then I can eliminate everything till that sequence and we can start a new partition. I think it will be linear anyway. Mhm. Okay, so direct binary search cannot be done on these things, I guess. Maybe even if you do, there's no advantage of that because you're not benefited in any way. Because you have to maintain the frequencies. But how to maintain the frequency? If you just okay, anyway, that will be linear again. Okay, the submission count is very less. I think this is a pretty good hard problem. Let's see. We, even few candidate masters are getting negatives in the fourth one. So I don't think